Hello everyone. In the previous chapters, we've been talking a lot about comparing two variables in a bivariate relationship to try and determine if there's an association between those two quantitative variables. And in this process, I've talked an awful lot about first graphing the data and then describing the relationship. So the things that we're describing are going to be the direction of the relationship, so positive or negative. We're describing the form of the relationship. So is it fairly linear? Does it have a curved appearance? Some other mathematical relationship? And then, of course, the strength of the relationship. The last piece that we've been describing, and I've urged people to be very cautious about calling something an outlier, but the last piece is describing any unusual observations. So today we're going to make an effort to identify what makes something an outlier when it's a bivariate relationship, and then we're also going to examine the impact that that has on our regression model. The data we're going to use to do that is the data set here on the screen. So it represents per capita consumption of cigarettes in various countries in 1930 and the death rates in number of deaths per million people from lung cancer for 1950. So there's 11 countries given. The US is at the bottom. 1,300 cigarettes consumed per capita, and then deaths in 1950 from lung cancer, 200 per million people. So the first thing we need to do whenever we're examining a bivariate relationship is we're going to need to graph the data. So in your Inspire, you're going to want to create a new document and you're going to want to add a lists and spreadsheet page. Each of these lists do need a title. So we'll put cigarette for column A, and we'll put deaths for column B, and we'll enter our data. And feel free to pause the video so that you can enter the data in your calculator and follow along with the work we're doing here. So we have our data entered. Now the next thing is to look at what the scatter plot shows us. So you're going to need a new data and stats page. And we're going to want to plot our explanatory variable on the x-axis and our response variable on the y-axis. So in general, the relationship that we observe is fairly linear, with perhaps one unusual value on the right-hand side here. And if you hover your cursor over that observation, you'll see that it's the ordered pair 1300, 200, which belongs to the US. The relationship aside from that point seems to be at least a moderate linear relationship, and it's positive. So as the per capita consumption of cigarettes increases, so does the deaths per 1 million people from lung cancer 20 years later. The next piece in analyzing the data is going to be to look at some of the diagnostic criteria. So the first thing we're going to want to look at is our R value. Back in our spreadsheet, select an empty cell, and you can select Menu, Statistics, Stat Calculations. Oops, try that again. Statistics, Stat Calculations, and then we're going to do two variable statistics. Our X list is going to be cigarettes, Y list is going to be deaths, and you should be able to leave the rest of the items here as they are and say OK. So we see an R value further down the list of 0.737, so about 0.74, which tells us that there is a probably moderate positive linear correlation between cigarette usage per capita and deaths per million. So now the question is, what about this value for the US? if we look at our scatter plot, it clearly falls outside of the pattern of the other points. So in order to examine its effect, the first thing we're going to do is we're going to go ahead and run a regression on the data we already have. So if you go to Analyze, you should have the option to show linear. And there is our regression equation. Uh-oh. Let's try that again. I accidentally deleted it. If you ever make a mistake using the Inspire, it actually uses the same shortcut for undo as your computer. So you can always hit Control Z and you can actually undo your last operation. So let's go ahead and record this regression equation. So just using symbols first, y hat equals about 67.56. I'm going to round to 2 places, plus 0.23x. And if I'm not happy with using the variables, instead I can go ahead and translate this into some words. So we can put the names of our variables in. And this is really a good practice for the AP exam because otherwise you're going to have to define your variables separately. So there's our regression equation. And we'll double check our R value. Our R value is 0.74 approximately. All right. So now we might be interested in saying, well, what happens if I remove this observation for the United States? And the Inspire will let us do that very easily. I can go back to my table and I can delete the values in this last row. So now I've deleted those, and you'll notice it automatically changed our 2 variable statistics. So the first thing that I notice is the R value skyrocketed. Let's go back to our graph and see what happened. You'll notice the regression equation changed, and it didn't just change a little bit, it actually changed an awful lot. So let's record this new regression equation and we'll compare them. So our new equation is going to look similar. We'll still have the same variables. But we'll notice my equation disappeared. Let me bring that back. There we go. So the first thing I see is that my slope increased and my y-intercept decreased significantly. Still rounding to 2 places. And our R value is 0.94. So what we've just observed is the impact of what we call an influential point. An influential point is a point when omitted from the analysis will give us a very different regression model than we began with. It's not as precise as when we're looking at a univariate distribution and we use Tukey's 1.5 times the interquartile range rule to definitively say whether or not something's an outlier. Instead, sometimes when we look for an outlier when it's a bivariate relationship, we have to try removing the outlier and then redoing our regression to ask ourselves, did it change significantly? Now, influential points are not the only points that we're interested in. We're also interested in something called a leverage point. So here we have an example of a relationship with body weight on the x-axis and brain weight on the y-axis. And these are various mammals, and a few of them have been highlighted for us. So for example, if we look at the hippo has an unusually large body weight but a fairly low brain weight. If the hippo value was removed from this regression, what we might almost predict is that our regression line would probably move upwards. So our slope would probably increase, and we would probably end up with a stronger linear relationship. Perhaps in this case, one of the more interesting points is the elephant. The elephant is what we would call a leverage point. While the elephant, being way out here with an unusually large x value, probably doesn't change the regression equation much, it probably artificially increases the value for our. While this elephant point has the potential to change our regression line, it doesn't really use this potential, but instead what it's going to end up doing is it's going to end up strengthening our correlation coefficient. Now, it may seem a little bit confusing because we have influential points, which, if removed, would give us a different model. And then we have leverage points, which, if removed, may or may not give us a different model. What's important to realize is that influential points is a term that's usually used for both of them. It influences some value in our regression. So maybe it influences our slope, maybe it influences our y-intercept, maybe it influences our r or our r-squared value. What's important is that we realize that each of these points have an effect on our regression problem.